So we're moving on now in Physics 2 from the fluid dynamics of Chapter 12 to now the Newton's gravitation in Chapter 13. We have two masses. There is a separated by a distance r. Then there is a gravitational force between these masses, and that's just given divided by the distance squared, where g is the gravitational constant. What is that? It's 10 to the, I think it's minus 11, something or other, every of the units. And this force, it is a force, so it has a magnitude and direction. The force is always attractive. Gravitational force on 2 is in this direction, on 1 is in this direction, and that's pretty much it. There's another important aspect to gravitational force, is that it's conservative. The work that it does not depend on the path taken, and so there's a potential energy associated with it, and that is, well, yes. This right here. This is the work done by the gravitation. Well, the work done by the gravitational force to bring one mass, AM2, from infinity up to this distance from M1. This is the potential energy. And so if there are no non-conservative forces working, then energy would be conserved, energy before it equal to energy after, including this potential energy. That's the potential plus kinetic energy. And that's where one would use this expression for the gravitational potential energy. Let's look at one problem, 13.8 from the text. Problem 13.8, an 8 kilogram point mass and a 12 kilogram point mass are held in place 50 centimeters apart. A particle of mass m is released from a point between the two masses 20 centimeters from the 8 kilogram mass along the line connecting the two fixed masses. Find the magnitude and direction of the acceleration of the particle. So we have a picture like this, called M1 and M2, the first two, and along the line connecting them is another mass. They're separated by a distance 50 centimeters, 0.5 meters, because I'm casting here, and 20 centimeters from M1 is this other mass, call it M. So 30 from the others, like so. And what are we asked? Let's let this be the x-axis, and M1, hold M1 at the origin, 0. And want to find the magnitude and direction of the acceleration of the particle. So you know that's F equals ma. The particle we're talking about here is m. So what are those forces? Force, I'll try again. Force in the x direction equals, gravitational force is always attractive. So let's look at just the magnitudes minus the force from the first mass, it's in the negative x direction, plus force from the second mass, that, and just put in what we have for the gravitational force between two masses. over, call this R1, the distance from M1, and call this R2, the distance from M2. Sum of the forces, these are the ones, equals MA in the x direction. And we want to solve this then for A. Which we can. The M, oh boy, M cancels out of the observation mass cancels out, unsubscripted mass cancels out, so that's G. 2 square minus M1 or 1 square. And now we can put in the numbers. Was 11, like so. And may as well do a little simplification here of what we can. There's that 12 over 4 minus 8 minus over 9, and combining those factors of 10 looks like that's minus 11. How does it go? A plus 2, or 10 to the plus 2, 10 to the minus 9, or common denominator, all of that. Why is all of this this algebra of any use? The fewer entries you make in the calculator, the better your chances of not making a mistake. So that's why all this algebra. And now I think we can use Google Calculator to see what we get. Here we are. And so, what is that? Minus 9, I think it was. Oops, clear. Okay. I think that was it. Yes. So yes, 1.410 to the minus 8, 7. Yeah, 10 to the minus 8 meters per second squared for the acceleration. That should do it. All right.